Hello, good evening. Let me teach you about LT software simulation procedure. First, we have to click on the after installation. We have to click the LT size software like this, and then File, New Schematic. This is a new schematic page. In this page, we have to design the circuit. Here, Edit, we will have component there. Click on the component. The components which we need can be selected from the list of components given here. Let's design an inverter circuit. This is an CMOS P circuit. CMOS P. I have given a CMOS P there. Now we have after CMOS P, we have to add an NMOS circuit. Edit, component. This is NMOS. Open. We have an NMOS there. So basically we need NMOS circuit and PMOS circuit for designing an inverter. Now drawing a line, PMOS should be connected to VCC and NMOS should be connected to ground. So this is a basic thing which we learn in VLSI. Now for giving power supply to this circuit, we have to edit, component, go to the voltage sources there. There is a voltage there. Produce a voltage circuit. Click on that. This is voltage sources can be connected to the NMOS circuit like this. There is a ground and up there ground we add up here. Now we have NMOS and PMOS, CMOS N and CMOS P here. As we are designing in LT Spice software, we are going to our project is mainly based on 180 nanometer technology, so we can here provide length and width of transistor whatever we have to give. So length for PMOS is 3.6 U and 1.8 N. Okay. For NMOS, right click, we have 1.8 mu. So after providing this, for 180 nanometer technology, the voltage for logic 1 is 1.8 volt. We will give 1.8 volt here. Now we have to provide the inputs for the circuit. Let us connect these two lines. There will be same input for an inverter. This is an output. Let us assume this is input and this is output. Now for simulation, we have to edit simulation command. Whatever stop time we require, we have to add that. This is the stop time there. Stop time, let us give us 10. Time for starting data 0 N or 10 N. Maximum time step is 1. Okay, we have an component like this. We should place that. Now as we are having an 180 nanometer technology, we have to include the file. So let us include that .op here. We have to write include dot include TSMC 180. Whatever the file, let me show you the file there, like 1 second. File name is tsmc.tsmc0118.lib. we have to add this file to the LTSpice software, so we will include that also. LTSpice op dot include TSMC 18.lib. okay, we have to place it there. Now for simulation, what we have to do is, after finishing this circuit, we save the data, and by clicking simulate run, we can simulate. If we want to edit, if we have mistake TSMC 0118, TSMC 018 live, okay, now save, run. We have to paste this file into the LTSpice software program files, LTSpice library files, sub. We have to place all the library functions here. Let us paste just here. Now let us run this. So we have got an output waveform kind of structure. Now let me zoom this circuit here. When we click the input, the pulse is, we can get the waveform here. The output is getting here. 1.8 volt is the given voltage value, 1.8. The output is 1.8. 0, we are giving 0 as input, and output we are getting 1.8. so we have made an inverter circuit possible. We can see 0 and trace 1.8. This is how inverter circuit is designed. Now let me, after giving connection, let me explain you about the FIR filter diagram, whatever we have designed. Zooming there, only I am zooming this part. So I have this circuit there. This is the D flip-flop diagram. These are the multipliers which have 4-bit input. This will be X of n, this will be H of n. We have an output of 8-bit plus 1 carry bit which will be generated here. So there will be 8-bit multipliers. These are both multipliers. This is the adder circuit. Now let me show how this diagram is possible. Basic FIR filter diagram have the same. Let me open each and every block and show you what is the circuit there. This is the D flip-flop. We have designed a D flip-flop like this. Each and every block contain a D flip-flop. This is a diagram for D flip-flop, in which we have designed D flip-flop 4 D flip-flop included in, and we gave it as an D flip-flop here. This is the 4-bit D flip-flop circuit. This is the 4-bit D flip-flop circuit. Now let me explain the multiplier circuit clearly. This is the multiplier circuit. Each and every input x0, there will be two numbers for multiplication, x0, x1, x2, x3, and y0, y1, y2 and y3. Using the multiplier adder circuit, we are going to generate the multiplication output in the end. Now this is the carry save adder, where we have used full adder circuits and carry generated circuits. Full adder circuits have this diagram, and carry generator circuit have this diagram. Carry generator, as we all know, AB, BC, CA. Basic diagram with an inverter here. We will get an carry before the summer generates the sum, so we can easily reduce the time for our implementation. So I'll close all that again. Now this is the 4-bit a single bit FIR filter diagram. We are assuming the inputs here. This will be the assumption of the input whatever we have designed. This the input should be designed with the proper FIR filter implementation. Now we have D flip-flop here, multiplier circuits here, and the carry circuit here. Let me simulate it. For simulation, it will take around 2 to 3 hours for 1-bit simulation. Let me run it. So after running, you can see here that it is showing that doing Newton-Raphson iteration for the DC solution, fill-ins 0. This will start. Here it is G minimum. This G minimum should go in the 10 to the power of 13. After that the second step is started. Now we can see that the G minimum has reduced to 10 power minus 3 after 20 minutes of time. We can see that G minimum has reduced here. It is getting reduced. This is the first step of the simulation, which will take around 1 hour to complete with the sources off also. This is the G minimum. It is getting reduced 10 power 3. It has to go till 10 power 13. Then the next step will get started. Now it's 1 hour time after the simulation has been started. We can see that the G minimum has reduced to 10 power minus 9 here. See, it has to continue till 10 power minus 13, so that the next step starts without the source. The next step will be the G minimum calculation without the source elements. It's been 2 hours, and now the second step has been started. Source stepping, trying to find solution with sources off. So sources are going to be off here, and G minimum is reducing here from 10 to 5.12. This G minimum has also to be reduced till 10 power minus 19, 10 power minus 14. Then we will get the third step. Then the source will go on to the simulation process. It's been 3 hours now. The third simulation process is started. This is the third step. Simulation time, transient analysis done is equal to 0.0%. Speed is that. So this is the third process. Here simulation time is increasing, means then the simulation will be continued after this much seconds. We can see that the simulation has been ended now. The simulation result has been produced here. Now we can see I have added some 9 traces. First output will be shown in the first trace. This is the first output. Second one here. Third one here. Fourth one. Fifth one. Sixth one is here. Seventh one. Eighth one. Ninth one. All we can see that these are the traces we are getting for FIR filters. Now this is around 0, this is 1.8, this is 1.8, this is 1.8, this is 0, 0, 0, 1.8, 1.8 and 1.8. These are the traces possibly we are getting here. This is the final output of FIR filters, whatever we are getting. And this concludes the demo. After the 7 nanoseconds, we can get the output waveforms like this. There are 3 cycles. Third cycle is going to start it. As I have given the 100 nanosecond time, so it is continuously going on. This is the output after 7 nanoseconds.